Good afternoon. My name is TJ Willits with Veolia Water Technologies, and I'd like to welcome you to the second edition of our webinar for anaerobic operators entitled Operational Efficiency of Anaerobic Reactors for Wastewater Treatment. I just have a few housekeeping items to discuss before we begin the webinar. You should be hearing me speak right now. If not, you could use one of the two audio options to connect to our webinar. One is using your computer and the other is obviously using the telephone. So you could call in using the information in the webinar panel, usually on the right side of your screen. This webinar is being recorded and it will be distributed for a replay a day after the seminar. So tomorrow you'll receive a note in your email of how to watch that seminar. And in terms of questions, we have a question box in the GoToWebinar panel on the right-hand side. Please feel free to use that panel if you have any questions throughout the webinar or at the end. And if time allows, we'll try to get to all those questions that you would put in that panel. So feel free to use that. In terms of requesting certificates, there will be a survey after the webinar. Not only does that survey provide you an opportunity to put some suggestions of content that you would like to have presented as a part of these continuing education webinars. If you would want to request a participation certificate for your continuing education credits, you would have to go ahead and request it on that survey, and I'll email one out to you in the next week or so after the webinar. So feel free to do that. Okay. I'm going to introduce your speakers. We have two speakers here joining us today for this webinar. Our first presenter is Greg Rosenberger. He is the manager of Veolia's Process Engineering Group, focusing on anaerobic and biological wastewater treatment systems. He is responsible for developing solutions for industrial wastewater applications, including the process selection design, mass balances, lab testing, and startup of these facilities. He has over 15 years of experience in biological wastewater treatment in a broad range of industries, including food and beverage, pulp and paper, chemical, ethanol. And in his career, Mr. Rosenberger has been everything from a process engineer to commissioning engineer and project manager on several anaerobic projects. Also joining us here for the webinar today is Ms. Jill Jordan, who has over 35 years of experience in the anaerobic treatment market. And is experienced with treating wastewaters using UASB, EGSB, CSTR, and anaerobic membrane reactors. And a fun fact about Ms. Jordan is she was actually on the startup team for the very first UASB system that was installed in the United States. So she has a lot of experience and has started up over 60 facilities in her career. So let's welcome our presenters here, and first to join us will be Mr. Greg Rosenberger. Greg.
Hello, everybody. Thank you for being on the webinar today. So we'll just go over the agenda topics that we will have. We'll start off with just a very brief review of what we touched on in the first webinar of our series. Then we'll look at the different types of anaerobic reactors that are out there, because there's people on the call here that have high-rate granular systems, or CSDRs, or anaerobic MBRs, or CSDRs. And then we'll get into the bulk of what the webinar is about, is really the testing requirements and some of the day-to-day laboratory and other control aspects that a operator should be doing when they run their anaerobic treatment facility. So just to quickly touch on the last webinar, in case anybody wasn't on it, or just a quick refresher. You know, when you talk about anaerobic reactors and anaerobic digestion, there's a lot of different types of bacteria in the system that all work together in harmony. The main two being the acid formers and the methane forming bacteria. The methane forming bacteria are the most sensitive of that bacteria, and are the bacteria that you need to keep happy in your system in order for the system to work well. If not, then your system will start to build up volatile fatty acids, VFA, and that's one of the key indicators that your system is becoming unbalanced. And there's several keys to anaerobic treatment that you need to keep in line, including controlling the food or controlling the COD load to the system, keeping the pH of the system in around neutral pH, keeping the temperature in mesophilic range from approximately 90 to 100 degrees Fahrenheit, give the bacteria the nutrients that they need, not just the macronutrients of nitrogen and phosphorus, but also a micronutrient solution. And of course, try not to put any inhibitors, biocides, etc., down the drain that would prevent the biological system from doing its work. So to transition in, we're just going to go quickly into the different types of reactors that are out there. A lot of people on this call have granular systems, the UASB and EGSB systems, but there are different types of systems out there. Each of them have their particular niche in the market, mainly revolved around what is the incoming COD or BOD and what is the TSS and FOG levels in the influent. And really the main difference in these reactors is the type of biomass that is in there and how the biomass is held within the system. You know, all biological systems work on a premise that the biology does the work, and you need to figure out a way to keep the biology in the tank. So a lot of these systems just have different ways of clarifying the biology to keep it in the reactor in order to do that COD and or TSS reduction. So we like to classify here reactors as sort of three different main types. You know, we classify them as high rate, medium rate, or low rate. In high rate systems, those are your granular systems, the UASB system and the EGSB system. UASB is the upflow anaerobic sludge blanket. EGSB is the expanded granular sludge blanket technology. You know, the biothane and biobed technologies are the trademark for the Veolia technologies in these realms. Then you have medium rate technologies. These are your anaerobic contact processes, which typically include a mixed CSTR vessel and some kind of a clarifier on the backside. That clarifier can be a traditional gravity settling clarifier, or it could be a DAF, for instance. The newer technology on the marketplace is the anaerobic MBR technology, which actually uses membranes as the biological separation. That is a trade name for Veolia. It's called membrane. And finally, for extremely high COD and high TSS applications, it's a traditional CSTR, just a continuous tank reactor. It's also the type of reactor you see in most municipal solids digestion applications. So really, we typically classify our systems into three: high rate, medium rate, or low rate. Really, that's about the loading rates that you can put into them, and then the influent decides which one of those technologies is the most applicable. So where do we use these technologies? Typically, the high rate technologies are used on low TSS type of influence. Typically, the TSS is less than 1,000 to 1,500 ppm, most times below 500 ppm, and with CODs up to about 25,000 milligrams per liter. So a high rate system, it's for soluble COD reduction. The influent TSS really just passes right through the system, so it only removes the soluble fraction, and typically about 80 to 90% in the food and beverage industry, typically around 90% SCOD reduction is what we see. If you're looking for more of a TSS or FOG reduction, then you need to go to longer retention times in your system, and that's where we get into the medium and low rate technologies. They're for higher influent TSS and FOGs. I mean, you can have FOGs that are up to 500, 1,000, 2,000 ppm. You can have TSS concentrations that sometimes go all the way up to 1 or 2%, 10 to 20,000 ppm. Both of the medium rate technologies uses sludge recirculation, so that allows the HRT of the system to be decoupled from the SRT. So So you can have an HRT, the hydraulic retention time of the system, be as low as 1 to 2 days, but your sludge retention in the system might be as high as 25 to 50 days. So that's what allows you to get your destruction of suspended solids and FOG in those systems. And finally, you have the traditional CSTR, which is really a once-through system. The HRT equals the SRT. Typically, you're talking about 20 to 30 days of retention time. These are big, large, mixed reactors, and they're typically used for very high-strength COD above 50 to 100,000, and usually with very high TSS, almost slurry-type waste. You'll see these in the manure industry and the municipal solids digestion industry. Occasionally, you'll see them in the food and beverage industries, more on waste type of product systems. So now we're going to turn it over to Jill, and she's really going to get into the bulk of the presentation today, really surrounding on what is the testing you should be doing and what you should be looking for. Jill?
Hey guys, glad to be back here with you. So let's talk about testing. Why are we testing at all? Well, the bacteria can't talk to you to let you know how well the system's working. Can't tell you whether it's upset or not. So the only way we know that is to test the various streams around the wastewater treatment plant or the reactor, and also the activity of the sludge. So we need to do this testing so we can determine if these 5 important indicators of system performance, food, pH, temperature, nutrients, and toxins, are in or out of the design operating range. Next. So let's briefly look at what's going to be tested or what we need to test. And I've broken it up here into 3 different categories. The first is what we measure in line, or readings that are taken at the wastewater treatment plant. The second are in-house analytical testing. So this is testing you would do. You go out and take some samples from somewhere and do this lab testing. And the third is outside lab testing. And mainly these are testings that were done in an outside lab because they're too complicated or require very expensive equipment that most wastewater treatment plants don't have. So on the inline measurements, we're doing things like temperature, pH, oxidation reduction potential, all the liquid flows, the biogas flow, the biogas quality, and chemical use, along with any biomass sludge additions or subtractions that may be warranted. On the in-house analytical testing, we do the testing for VFA and alkalinity. Remember, VFA is the most important test we do to determine the system's health. We also do COD, various solids, and the nutrients, nitrogen and phosphorus, and also we'll do sulfate because of the sulfur-reducing bacteria we talked about last time. The outside lab testing is done for BOD and micronutrients, because the BOD testing is a pain in the neck to do, as we all know, and also very hard to get done properly. And also the micronutrients are also sent out to be done by an outside lab because they require usually a mass spec to get the, or atomic absorption to get good results. So we're all on the same page, and we're all talking about where samples are taken to do this testing. Let's look at several different designs. Now, some of you that have our first generation EGSB and UASB systems, if you look up in the upper left-hand corner of this slide, the influent goes into an equalization or conditioning tank, depending on what you called it. Then it was fed into the reactor, and the effluent recycle went back to the EQ tank, conditioning tank. Biogas and sludge obviously came off the reactor. In our new flow diagram, which is the middle drawing, we have raw wastewater goes into an EQ tank, and the influent then comes out of the EQ tank and goes to what we call a rapid mix tank. Then that's fed into the reactor, and the effluent recycle comes back to the rapid mix tank. Again, the biomass and the biogas come off the reactor. So those first 2 are really the primary flow diagrams for our UASB and EGSB plants. The bottom left drawing, it refers to our CSTR type lower rate systems, where the raw wastewater goes into an EQ tank, and again, the influent comes out of an EQ tank and into the continuously stirred tank reactor. The biogas comes off. Now, in the really low rate systems, once passed through that Greg talked about, the effluent and the mixed liquor just come off the reactor. If we're returning sludge to the reactor to get better solids breakdown, we take the mixed liquor and it goes to some sort of separation process. That could be a membrane or a centrifuge or a DAF or something like that. If it's a membrane, the retentate, which is the concentrated sludge, goes back into the reactor, or it can be discharged. And the permeate is the final effluent, which is really super clear, nice, clean water. If it's a centrifuge or a DAF, those solids come off those equipment and is discharged or sent back to the reactor, and the effluent comes off either the DAF or the centrifuge. So let's look to see where and how often we do testing. So let's start with the inline measurements. The pH and the temperature are measured inline on the raw wastewater, the influent, the reactor feed, the effluent, and or permeate. And that's done daily. So they're inline, they're measuring all the time. Similar for the oxidation reduction potential, in that it's measured all the time. But that's really, we only need that really on the influent and the reactor feed. The liquid flows that we measure are the raw wastewater, the influent, the reactor feed, the effluent, and or permeate. And again, that's daily inline measurements. The biogas flow off the reactor, measured all the time, daily off the reactor. Same with the biogas quality. There's the new gas flow meters, also measure the percent methane at the same time, or the operator has to test the CO2 and hydrogen sulfide content of the biogas daily to back calculate the methane content. Chemical use should be recorded every day so you know how much you're using. You know that the guys up at the accounting department need to know that. And it's also good to know how much you're adding so you know how much, especially with the nutrients, if you're putting in the right amount of nutrients. Sludge additions and removals are obviously just measured when that's done and on an as-needed basis. So on the in-house analytical testing, what are we testing and how often? The volatile fatty acids and alkalinity and the total COD are measured on the influence, the effluents, and or permeate on a daily basis. The soluble chemical oxygen demand is usually just done on the influence and the effluent on a daily basis. Total and volatile suspended solids are done on the influence, effluent, permeate, and on biomass samples or mixed liquor suspended solid samples on a daily basis. For the mixed liquor, for the biomass, usually done on the high rate systems only about once a week or every other week. Settlable solids. On the high rate system, they're measured on the influent, the effluent on a daily basis, and also can be done on the mixed liquor suspended solids on a daily basis if required. The nutrients, which are at the bottom here, they're measured on the influence and the effluent, and usually just once or twice a week. Just once a week, if you're not adding these for nutrient purposes. If you're adding them, it's better to do it a couple times a week just to make sure that you're keeping up with the requirements. Outside lab testing, BOD, influent, effluent, permeate, and it's really what's required is permitting. We don't really use these for controlling the system, but it's necessary for permitting, so that really defines when you, how much you need to do this testing. We also do it more often when we first start up a plant so that we can get a ratio between the COD and the BOD. The micronutrients are done on the influent, the effluent, the biomass, mixed liquor, and that's usually done about 2 times a year. So all these tests, what do the answers need to be to ensure that your system's working well? So the most important test is the VFA test. On the influent, it's variable. It can be all over the place depending on what your wastewater is. But we monitor it to determine the pre-acidification, especially now that we have these, that we use EQ tanks more frequently. And we'd like to see about 15 to 30% pre-acidification in the EQ tank before the water goes to the reactor. On the anaerobic effluent, the volatile fatty acids should be less than 5 milliequivalents per liter to ensure that the process is stable and working really well. And if it's working really well, it should be 0 or 1 or less. And that's, most of you guys know that that's what you can get on most of the time. If you get between 5 and 10 milliequivalents per liter, you should start looking to see what's wrong and why. And if it's greater than 10, you really need to take a very strong look to see what's going on and why and fix it as soon as possible, because that means the system is really out of control. The alkalinity test most of you are doing is a test that the alkalinity is also a result of the VFA test. And on the influent, it's close to 0, unless there's a lot of CIP water coming down or there's a lot of lime or something like that used in the process. On the effluent, we want at least 20 milliequivalents per liter of alkalinity. This will ensure that if the system starts to get high VFA, that the pH won't change, because before the pH changes, the VFA has to use up the alkalinity. Will be balanced by the alkalinity. So if you have like 20 milliequivalents of alkalinity and your VFA comes up, it'll be a while before the pH comes down. So if you have a VFA problem and your pH goes down, it's a double whammy, and you don't want that. I think you can remember from webinar number 1 how important the pH and the temperature are. The influent pH and temperature can vary all over the place, and we're going to control those in the process. So what we're shooting for in the effluent is a pH of like 6.8 to 7.2, which is where we get our highest methane activity. And the effluent temperature, the reactor temperature, needs to be about, as Greg said, between 90 and 100, but we like to keep it around 98 or 37 C for the highest activity in the biomass. This influent COD and BOD. This is a tough one because it can be anything, and really the systems are designed based on what the COD concentration is. So if you have a COD concentration greater than 20,000, you might be considering one of the CSTR reactors. The UASB and EGSB reactors, these high rate systems, typically have a COD or BOD of less than 25,000 milligrams per liter. And why is that important? Because if it's greater than that, the hydraulic retention time of the influent in the reactor would be more than 48 hours. And if it's more than 48 hours, granulation is not, well, the high hydraulic retention time limits the amount of granulation. So you want to keep it below 48 hours so that you get good granulation. Now, the COD to BOD ratio can vary all over the place, but typical for the food and beverage industry is about 1.6 for the influent water. And that ratio will increase on the effluent. Could be 2 to 3, maybe even 4 at some times. For the chemical industry, pulp and paper, things like that, the COD to BOD ratio on the influent can be as high as 3 at times. The solids. Again, the type of process you are dealing with determines what kind of influent solids you want to look at. For the UASB and EGSB systems, you don't want your influent TSS to be more than 10% of your total COD. So if your COD was 5,500 milligrams per liter, you wouldn't want your TSS to be more than 550 milligrams per liter. And that's because you don't want the influent solids to be greater than the potential sludge growth in the reactor. If the influent solids are greater than the potential sludge growth, eventually the solids in your reactor would be all of these influent solids, and you wouldn't have any biomass in there. Wouldn't work very well then. If you have higher solids in the influent, you're going to be wanting to use a CSTR anaerobic membrane reactor or lagoons, as they can handle the solids, and actually you can get some solids digestion out of them. On the effluent TSS, for the high rate systems, the effluent TSS should not be more than the influent TSS. On the lower rate systems, they're going to be higher until you get to the separation point. And at that point, depending on how well the separation system works, it should be very much significantly less than what the influent was. If you get to the membrane bioreactors, there are actually like no solids in the permeate, which is really good. We also look at the settlable solids in the high-rate granular systems because we want to make sure we're not losing granules. So we'll grab effluent sample of the reactor effluent, put it in an Imhoff cone, and watch it for 5 minutes and look to see how many granules have settled in that 5-minute period. And as long as you have less than a milliliter per liter of granules in that 5-minute settling test, you should be good, and you should be retaining all of your granular biomass. Macronutrients. First of all, we test the influence, and we want to see how much, if there's enough, okay? So we look at the COD to nitrogen to phosphorus ratio, and if that ratio is good, somewhere around 1,000 to 5 to 1, there's no need to add anything. But if it's not that, you're going to need to add nitrogen and phosphorus. And you're going to want to add it until your effluent ortho P is greater than or equal to 5 milligrams of phosphorus per liter. And you also want to add nitrogen to the point where it's greater than 10 milligrams of nitrogen per liter. The micronutrients. Again, the amount that is required is proportional to the COD concentration. The higher the COD concentration, the more micronutrients you need to add. The table here lists the various micronutrients and how much is required based on the COD concentration. Once you have your influent sample tested, we usually recommend that you collect a 10-day composite influent sample and have it tested for the micronutrients. If it's less than any of the values here, you need to add that particular mineral as a micronutrient. Biogas composition. A lot of people put stock in the methane quality as telling you how well the system's working, but that's not always a good deal because the methane can range from 60 to 80%. The carbon dioxide concentration in the biogas could be between 20 and 30%. The water vapor, depending on where you take your sample, could be between 1 and 4%. And the hydrogen sulfide concentration is going to be dependent on the influent sulfur. Now, generally speaking, about 50% of the gas made in the reactor will be carbon dioxide and 50% will be methane. In general, that's not always the case, but in general, that's a good assumption to make. But the CO2 can be absorbed in the water, and the methane isn't able to be absorbed very well. So the amount of CO2 that can be absorbed in the wastewater determines how much solids can be, how much methane is in the biogas. Sorry, guys, I just lost my yeah, we're good. Okay, next slide. Okay, give me a second here, guys. Okay, so let's finish up with the, sorry about that. Anyway, the COD and BOD reductions. Again, that's going to be system determined, but in general, the soluble COD reduction that you see in your system should be 80 to 90%. If you have a wastewater with a high BOD to COD ratio, that could be less. It could be as low as 60%. But in that case, the BOD reduction should still be greater than or equal to about 90%. The total COD reductions that you should be achieving are based on your solids and your effluent. If you see the bottom equation, the total COD is equal to the soluble COD plus some X factor times the TSS. And that X factor is going to be dependent on each substrate, and each plant is going to be different. But you can see the more TSS there is in the effluent, the higher the total COD will be in the effluent, which result in a lower total COD reduction than soluble COD reduction. How do we know how much sludge is in the reactor? On the high rate systems, we do a sludge profile. And in that case, we take samples of biomass from various levels in the reactor, do a TSS, VSS test on that sample, and assume that that concentration of sludge is at that level to the level below. And then we add up the kilograms of sludge at each level to give us the total amount of biomass in the reactor. For CSTRs, lagoons, reactors, the lower rate reactors, we just measure the TSS and VSS of the mixed liquor suspended solids, which is in the totally mixed system, to give us the amount of sludge in the reactor. And why is that important? Next slide. Because we need to determine if the sludge is being overfed, and we do that by calculating the food to mass ratio. So the food is the amount of COD that went into the reactor, and the mass is how much sludge is in the reactor. So that's why we need to do the sludge profile and why we need to calculate the F to M. The F to M can range from 0 to 1 depending on the type of system that you have. It's typically about 0.5 for our higher rate systems, EGSB, UASB systems, and lower for the lower rate systems. Could be like 0.1 to 0.3 kilograms of COD per kilogram of VSS per day. And now I'm turning it over to Greg for the end of the presentation.
Okay. So when we look at systems, you typically want to keep your loading rates of the different technologies within a specific range in order to be stable, or when we look at designing a system. If you're looking at a CSTR system, typically they're the lower loaded systems, so we keep the loading rates typically in the 1 to 5, sometimes the anaerobic contact processes where we recycle biomass can go up to about 6 or 7. And this is all in kilograms of COD per meter cubed of reactor per day. So the UASB, a higher rate system, typically we load them in the 8 to 12 range. They can spike up to 15. And the EGSB systems can typically be loaded at the range of 15 to 20 with spikes up to 25. So essentially you look at your influent COD concentration and flow and your reactor volume, and that's how the system is originally designed. Or if you have an operating system, what your system should be in the range of in order to operate in a stable manner. Here's another calculation that as an operator you can do to try to look at the mass balance of your system and where all the COD in the system, actually that's the next slide, excuse me, this is methane yield. So the amount of biogas produced is directly related to the amount of COD that you reduce in your system. So if you're looking about doing some mass balances and trying to figure out, am I making enough gas? Is my biogas meter correct? Are my COD readings correct? You can take your mass of influence COD, your mass of COD in the effluent is really just a difference in concentrations. And for every kilogram of COD that you remove in your system or that you destroy in your reactor, there should be 0.35 meter cubed of methane gas created. I'll let you guys figure out how to convert from meters cubed to CFM, because probably most of your gas meters are reading in CFM. But if you do this type of math, you should be able to get a good correlation between the methane produced, which you can develop from your biogas flow meter, and your methane reading or CH2 and H2S readings, and the influent and effluent COD values that you have. So this is something you could easily input into a data sheet that you have, just to sort of have another checkpoint out there that when you put your data in, does the COD reduction match the biogas yield? And if for some reason that is way off, then you know you might want to look into some things a little bit more closely. Next slide. Another thing to look at is the COD balance. So that's what we were talking about a little bit before. It tells you a little bit how good of your analysis is and how accurate your analysis is when you're doing your system. Looking at your COD in, your COD out, your mass of your biogas. When you do that, it should come close. It's not going to be perfect. You're not going to get an exact value on a day-to-day basis. But if you calculate your COD removals and you calculate your biogas and you're off by 50%, then you probably have an issue. Is your gas meter wrong? Is your COD meter reading incorrectly? Or you're doing your COD measurements incorrectly or something? So it's just another check and balance that you have that really doesn't, can be done with the data that you should be taking on a routine basis anyway, in order to just have a little bit better understanding of your system. So just to look at a general summary of some things, I mean, the key thing to look at, especially when you're running an anaerobic system, is your effluent VFA. If you're only going to do one test, we'd say do the effluent VFA test. As we went through, there's a lot of different tests that you can run on a daily basis or on a weekly basis. We recommend a specific testing routine, but at the same time, if you're measuring your nitrogen every day and it's the same every day, you can start backing that off to once a week or once every 2 weeks. What is best for your system. But the effluent VSA is something that you should be doing pretty much on a daily basis because it's an instantaneous snapshot of where your system is. And if it's higher than 5, that probably means you have an issue going on that you're going to want to address before it gets out of control. Second, the two big things are pH and temperature. Most reactor upsets occur because the pH gets out of control or the temperature gets out of control. And these are typically done, measured online. So this is something that you should have maybe potentially some interlocks in your systems that prevent things from happening. And if it doesn't, you should make sure you're calibrating those instruments, because they're extremely important. Another thing is just overloading your system. If you're doing your influent flows and CODs, you know what your daily system is. You know what the system should be able to generally handle. First thing you look at if you come in and your VFA measurement is high, and your pH and your temperature have been good all night long, is what came in the plant yesterday? Did my load double? Did my load triple? That's something that you need to monitor. Usually when you have nutrient-related issues, they're more of a chronic, longer-term, medium-term issue. You'll see your system performance degrade over time, and you really can't tell why. All of a sudden your reactor's fine, your pH is fine, the loading rate to your system is within range, but you're just not getting the removal rate. You used to get 90, and all of a sudden you're getting 85, you're getting 80. Why? A lot of times we look at nutrient issues, nitrogen, phosphorus, but then sometimes micronutrients. Are you adding them correctly? And obviously, in the end, if your system is running very well, it's been running well for weeks and months and years, and all of a sudden, out of nowhere, your COD removal rates go down extremely bad, your biogas goes down to nothing. Most times that points to a toxic event that occurred. Something came down from the waste treatment plant that inhibited, hopefully it didn't kill, but inhibited your biology. Then you need to figure out a way to get rid of that in your system. Sometimes it's just flushing your system with a whole lot of water. Maybe it's lowering the loading rate to your system for a few days to have the biology come back, into range and into life. So those are some of the key things that on a day-to-day basis you will see when operating a plant that you want to maintain and review. And testing is important. I know sometimes it's a pain in the butt. Nobody likes to do the testing. But in the end, if you have no data, it's tough to identify problems and it's tough to control your system. So, data is our friend. Get as much data as you can, enough data that is reasonable, and record that data. You should be recording that data on some type of an Excel spreadsheet that you can keep. Maybe once in a while you print that out on a log, so in case somebody hits delete, you still have some back data, etc. But testing is our friend. Next slide. So just a little bit of an infomercial here. We have some new things that can help plant operators run the system a little bit better and or make it more easier to monitor. Veolia now has what we call Aquavista, which is a web-based Internet of Things portal that essentially takes the data from your PLC and will convert it into a web-based access platform. You know, it can be as simple as just being able to log in through the internet, being able to create some specific graphs that you want to look at, etc. You know, we can develop management reports. We can develop, you know, cost data information, etc. We can tailor it to your specific facility. And if you want to go all the way, we now have some online advanced instrumentation where we actually do online measurement of COD or TOC and control your whole plant with that, you know, greatly reducing the, you know, chance for upset, you know, eliminating a lot of day-to-day lab work that needs to occur, basically do it online, measurements and with some smart programming. So there is some new things out there with respect to advanced online control that if people are interested in, you can give us a call. We could review that with you. Next slide. Another thing is too is you know, we do aftermarket support. So if you have a system, we hope it's our system, but even if it's not our system, we do go out and do a lot of things aftermarket. We give training to operators. I mean, obviously when we start a plant up, we go out there for a week or sometimes longer to train the operator, go over everything in detail. You know, typically that operator doesn't stay there for 30 years. If you're a new operator, you know, we can come out and give a training. We do plant audits and optimization. If you have an older plant, you know, that you think maybe needs some upgrades, what's the latest, isn't running very well, we can come out and for a day and just review everything and then provide you with a report of some recommendations. If you need to expand your plant or upgrade your plant because you need a new aerobic system, you have tighter sewer limits, etc., we do that work. We also have our own in-house lab, you know, similar to the labs that maybe some of you have in your office, but a little bit bigger. We do biomass activity testing. So if you think your biomass is not performing like it should, you can send that in. We can do an activity test on it. If you have biomass to sell or you need biomass because you had a toxic event, we can get you that. We also do chemical toxicity testing. Some plants don't allow new chemicals into the production facility unless they can prove that it has a test report that says it's not anaerobically inhibitory or toxic. So we can do that testing as well in our lab to ensure that it is not. So we have a lot of support services that if you need something, give us a phone call. You know, the phone call is free. You can, you know, discuss some things. We can come out to the site. We can do some support over the phone, etc. So we're here. You know, we're located in Philadelphia area. So give us a call if you need anything. So that concludes today's webinar. We said we'd keep it at 45 minutes, and I think it's exactly 2:45. So we're going to turn it back over to TJ. He's going to go a little bit when the next webinar will be and then take any questions. TJ, you're on mute. TJ? Well, while TJ figures out his mute question, I will take the next webinar. So the next webinar will be in September. We haven't set an exact date yet, probably sometime in the second or third week of September. We have a couple different topics we're bantering about. If you have a specific topic you'd like to hear about, please email us and we'll discuss that and maybe include some of that in our next webinar series. So we hope you can make it. You should see probably a reminder of when the next one will be in a couple months from now. And then we'll set a specific date and you'll get the same reminders that you've been gotten for the last two. Is TJ back yet? Doesn't sound like he is. Okay, so from a question and answer standpoint, we have a question about converting meters cubed into CFM. So let me look here. I have a handy-dandy conversion program.
There are 35.3 cubic feet per cubic meter, so you can do it that way.
Another thing you can do is you just go online to our friend Mr. Google, and you type in conversion factors. You can actually find a lot of just online tables that, that's basically what I do. Is essentially just go online. Actually, you can go on your phone. You can get a free app that does conversions as well to have on your phone. But as Jill said, there's 35.3 cubic foot
per cubic meter.
Per cubic meter. So that's how we do that there. Okay, hold on a second. I gotta log in here and figure out the
next question.
questions. Okay, question about testing frequency, and do we really need to do that much testing? So the answer is yes. As Jill would say, Jill says yes. You need to do all that testing, and you should be doing it on Saturday and Sunday. Me being the more reasonable one says that typically what we suggest is that you do that level of testing for a certain period of time. DJ, are you okay? Now we're better. And then you can back off on that level of testing as your data shows that you basically have repeatability on a day-to-day basis. So in the end, if you only have so many hours in a day, do the testing that is you can do. VFA, COD, TSS is probably the core testing from a lab basis that you should be doing on a pretty frequent basis. Nutrients can be done once a week typically if you don't ever have to add them, maybe once a month. There's some specific stuff where you need to do BOD, just send them out on whatever frequent basis you have. But in the end, yes, you can back off on the testing requirements if your data shows that it's pretty repeatable on a day-to-day basis. But we would never say don't go to any data collection. It's always good, even if everything is repeatable, to always do a couple of measurements at least once a month so you have some back data to understand, if something differs from, the norm.
Greg,
DJ, you back? Yeah, we can hear you now.
Greg? Okay.
Yes.
Good. Sorry about that for those technical glitches. We do have a couple more questions if you don't mind answering them. We have one that is that we saw a lot of chemical indicators. Are there any microbial markers that could be used in terms of part of those tests?
There's really not any microbial tests to be done. That's
online. There's some things that are sort of out there in the academia world where they're trying to figure out how to do some microbial type of semi-online testing. I wouldn't say there's any that we have seen that I would spend the money on to actually do. From a microbial testing standpoint, I think your best bet is just to do some activity tests on your sludge. We do that in our lab. There's some other people out there that do it, where you can send a sample of sludge in, we can run an activity test on it, we can tell you what the maximum activity level is, and if you have one of those done every 6 months, then you will have a back case history that all of a sudden one day your system isn't working well. You have something to look at what it should be operating at. But we haven't found anything yet from a purely just sort of a probe or a, semi-continuous instrument per se.
Yeah, it's not like an aerobic system where you would take it under the microscope and make sure that you have a certain percentage of, higher forms and not too many filaments and not too many pin flock. It's not like that, especially with the granular sludge. With the granular sludge, it's don't know whether you mean microbial, but it's just visually you can look at it and tell whether it's good or bad sometimes. And on the CSTR, it's I've never seen anything that's just looks pretty much the same. Again, you don't want too many filaments in it or something like that, but it's really hard to control because your sludge age is so long in these systems.
Thank you. Another question that we have here is related to retrofitting an existing UASB system with a rapid mix tank. How complicated is that, and what kind of benefits could the site see by including that in the process?
Okay, so we actually have converted a couple plants from sort of a traditional conditioning tank where you recycle back to sort of a combo EQ conditioning tank into a pure EQ tank followed by a rapid mix tank. It's not very difficult to do. The rapid mix tanks aren't very big. Typically, they're shot fabricated tank, 8 to 12 foot in diameter, typically as tall as your reactor is. So typically, a lot of that work can be done offline. The tank can be set, the piping can be done, and then there's some tie-ins. The major benefit for you is obviously you gain some equalization tank volume because you no longer have recycle going back to it, so it's a way to gain some EQ tank volume. The other thing it allows you to do typically is get a little bit better pH control because you're dosing your caustic into your rapid mix tank. So instead of dosing it into a tank that maybe have 4 or 6 or 8 or 12 hours retention time, typically we size our rapid mix tanks between 15 to 30 minutes. They're a little bit more well mixed. So you potentially could see, if you control your pH better, that means that you theoretically should be able to save some caustic because you can control the pH a little bit in a tighter range. So the major benefits are EQ tank volume and some pH control improvements, which could lead to lower caustic values, lower caustic consumption rate.
Okay. A question here about the effluent NH3N. It's mentioned to be greater than 10 milligrams a liter. What would be the upper limit of that measurement?
Is that effluent?
Yes, effluent.
So you want the effluent ammonia at approximately 10 milligrams per liter.
And the upper limit depends on the type of system, but over a high rate system, it's typically you don't want more than like 1,000, 1,500. It gets to be sort of toxic. On the CSGRs, they can run higher than that with some adaptation.
So I mean, your effluent ammonia, we like to keep it at above 10. If you have to add it, upper limit, 1,000 to 1,500 systems for run at CSTRs, like Jill said. There's some out there that are up in the 2,000 to 2,500 with some adaptation. Now, one thing to note is if you're running along at 50 or 100 on a day-to-day basis, and all of a sudden one day you spike up to 1,500 or 2,000, you're going to see an issue. So a lot of times, if you have an ammonia concentration and you order of magnitude of greater because there's some kind of nitrogen dump in your system, that can actually act as a temporary inhibitor if that happens. So when you go up to higher ammonia values or high nitrogen values, typically it takes some adaptation time.
Okay, well, there's no further questions. Again, if you want to request a certificate for continuing education for this time, please do so on the follow-up survey that will be given to you right after you close out of the webinar and by email. We'd like to thank both of our presenters, Greg and Jill, for their time today and sharing their knowledge, and also thank you for joining us to learn a little bit more about your systems and anaerobic digestion. So at this point, we're going to conclude the webinar, and please stay tuned for communication for our next webinar in September. Thank you.
Bye, guys.